Welcome, students. In this first video segment for our semester, we're going to take a look at section 1.1, Systems of Linear Equations. I thought before doing that, it might be a good idea to talk a little bit about one of the two main topics of the course, namely linear algebra. The course covers two main topics, linear algebra and differential equations. And we're going to be bouncing back and forth in this semester between these two topics. The first topic, linear algebra, to get an idea of a really nice short definition, I went to Wikipedia, and Wikipedia says that linear algebra is the branch of mathematics concerning linear equations, such as the one there, a1x1 plus a2x2 plus a3x3, etc., plus anxn equals b. These equations are called linear equations again, and we can kind of see why they're called linear equations. If we assume that a3 through an are 0, the coefficients of the x's, and relabel x1 and x2 as x and y, then we have the equation a1x plus a2y equals b, and this is an equation of a line. So I have a feeling this is where the name linear algebra came from. So linear algebra doesn't necessarily have to do with studying lines, but equations that sort of generalize or are generalizations of equations of lines. If you've had calculus 3 already, you know that if we have a third variable, z, or x3 in terms of the Wikipedia equation, then we're looking at planes. So we're not necessarily looking at lines. We're looking at lines in 2 dimensions, planes in 3 dimensions, etc. Central to the topic or the branch of mathematics linear algebra are 2 very large items. The first are called matrices, and the second main idea or big idea is called vectors. These 2 topics are going to play a main role in the study of linear algebra. In fact, today we're going to, or in this video segment, we're going to see how matrices arise right away. And the chapters, I believe 2 and 5, are dedicated to studying these things called vector spaces. If you've had physics, and a lot of you have, if you've had physics or Calc 3 or both, then you studied some vectors, but the topic or the idea of a vector is much more general than the physics or Calculus 3 idea of a vector being an arrow in space. So we got a lot of work to do. So let's go back to the topic in this particular section, which is to study systems of linear equations. And if you're thinking, I've studied linear equations in at least 3 classes already, why are we doing this again? You're right, that's a good question. You saw linear equations first in elementary algebra, then you studied them in intermediate algebra, then you probably saw them again in pre-calculus. The topic of systems of linear equations is extremely important in STEM field mathematics. And again, this course is essentially an advanced engineering mathematics course, which really means that we're here to polish up the methods that you've studied in linear algebra previously, although you may not have called it linear algebra, specifically systems of linear equations, and to learn some new stuff. So let's take a look at something or an example that comes from elementary algebra. So this example comes from elementary algebra. So from elementary algebra comes our first example. Algebra. Suppose I have a kind of a simple word problem. I want to find two numbers. Find two numbers. That's not the whole problem. If that were the whole problem, it would be kind of easy to do that. But I want to find two numbers whose sum is 4. And if that were the entire problem, we would essentially be done, because there's an infinite number of pairs of numbers we could find that add up to 4. 0 plus 4, 1 plus 3, 1/2 plus 3 and 1/2, etc., etc. But there's more to this problem. Find two numbers whose sum is 4 and whose difference is 0. What this leads to, and I know you already know this. This is just an example made up to sort of segue into our more advanced ideas with systems of equations. But what I know, you know that this leads to a system of equations. I want to find two numbers that add up to 4. I could identify the numbers as x and y. So I think I'm committing a mortal sin here by not saying let x equal the first number and let y equal the second number, or whatever. But the idea here is just to sort of remind us of what systems of equations were in elementary algebra. So the two numbers add up to 4, x plus y equals 4, and their difference is 0. So when you consider the two equations together, that is, you consider the idea of finding two numbers x and y that satisfy both of these equations, you get what's called a system of equations. This is a system of equations. Okay, and I know you know that. Equations. The idea in this first section is to present to you ultimately some more advanced theory of systems of equations that you can apply in STEM fields, and to give you an actual couple of methods. Actually, we're going to look at several methods of solutions of systems of equations that are really applicable to the kind of technology that we have available to us. So let's dig into this. Let's dig into this topic a little further. We can rewrite this system in a couple of different ways. Okay, we can rewrite this system by, I'm still getting used to my surface here. We can rewrite this system by eliminating all of the variables and creating a rectangular array of numbers. We can construct from our system a rectangular array of numbers, a box of numbers, a rectangle of numbers. This rectangular array of numbers, this is called a matrix. In fact, this specific matrix is called the augmented matrix for the system. Augmented matrix for our system. We're going to be looking a lot at vocabulary, so don't get too bogged down with the terminology now. This is mostly just a really quick introduction to this section. We can also rewrite this system in a different way using this concept, still using this concept of matrices. The plural of matrix is matrices. So there's no word matrix. There's no word matrix, and there's no word matrices. The singular of matrix is matrix, and the plural of matrix is matrices. So we could also write this system in a different way using this kind of yet really undefined idea of matrix. A matrix. I guess I did. I said it was a rectangular array of numbers. So we could write this system as this matrix, and then right next to it we could write another matrix, xy, and another matrix on the other side of an equal sign for 0. And this is called a matrix equation. This is called a matrix equation. A matrix equation. Okay. And in both cases, we've really changed the way the original system of equations looks. In the first example, the augmented matrix, we've eliminated the variables entirely, And if you really think about it, a computer, if a computer used to solve a system of equations, doesn't need to be actually fed the variables. All the computer needs is to know what the coefficients of x and y are and what the constant terms on the right hand side are. Okay, so that's kind of where we're leading with matrices. This first in the matrix equation, this first matrix on the left, we often abbreviate with a capital letter. We can also abbreviate this matrix with another capital letter X, and we can abbreviate the matrix on the right hand side of the equation with another capital letter B. The A is referred to as a 2 by 2 square matrix. And so A is referred to as a 2 by 2 square matrix. X and B also have special names. X and B are called column vectors. Again, don't get too bogged down with the vocabulary. We're going to be looking at a lot of vocabulary, and it'll be introduced and reintroduced and reintroduced over and over through this section and the upcoming sections. So this is again mostly an introduction. But look at what happens with the last example here. If I use these the 2 by 2 matrix and column vectors to represent the system, I can rewrite the entire system as something that looks like AX equals B. And this looks like a linear equation from elementary algebra. Okay, where the A, X, and B, the A, the X, and the B, they're not real numbers. They're in fact these more general concepts of or general things called matrices. Okay, so in this section and more generally in the course, we're going to be considering solving a general system of equations with M equations, M as in Mary equations, and N unknowns. So let's assume that the N unknowns, they're not X, Y, Z, etc. We kind of quickly run out of letters. They're X1, X2, X3, all the way up to X sub N. And then our first equation might look something like A1, X1 plus A2, X2 plus A3, X3 plus dot dot dot, all the way up to the coefficient of that last unknown, A n X n equals, let's say, B. So there's one linear equation with n unknowns. So we need a whole bunch more equations. We have M as in Mary equations here, and that's just the first one. So we need another n coefficients. Well, I've used A for the first coefficient. I could use B's for the second coefficient, but then I'd quickly run out of letters. There are only 26 letters in our alphabet. So we're going to use A's again as the coefficients. Okay, but we're going to have to change things up a little bit. We can't do this. We can't write the second equation as A1 X1 plus A2 X2 plus A3 X3. We can't do this. Why not? It looks exactly like the first equation. And that's not good. It's just the same equation. So to differentiate the coefficients between the first and the second equations, we're going to put another subscript onto the coefficients. So we're going to call the first coefficient in the first equation A1 1, and the second one A1 2, and then the third coefficient A1 3. So the first subscript is indicating which equation we're looking at, the first equation, and then the second subscript is indicating that we're looking at the coefficient of that variable. So A1, 3 is the coefficient of x3 in the first equation. So the coefficient of xn will be A1 for the first equation and n for the second subscript for the nth variable. And we're going to have m equations, so we're going to need to just do something on the other side with b. So we'll say b1. So the second equation will have b2, and then we change the coefficients to include double subscripts to accommodate that we have a whole lot of equations to write out. So what will the coefficient of x1 what will the coefficient of x1 be in the second equation? Will it be a12 or will it be a21? Well, if you caught what I said about the first equation, the first subscript tells you what equation you're talking about. So it's a21, and then a22, and then a23, then what's gonna be the coefficient of the last variable, ax sub n? Well, it's still the second equation, so it's a2n xn equals b2. So the third equation will look like a31 x1 plus a third equation coefficient of x2, a third equation coefficient of x3, so a33 x3 plus ... all the way up to a third equation, nth variable equals b3. And let's write ... Let's skip down to the last equation. The last equation is going to be which equation? Is it the M as in Mary equation or N is in Nancy equation? It's the M as in Mary equation. So it's M as in Mary, but it's the coefficient of the first variable. So am1 x1 plus mth equation, second variable coefficient, plus mth equation, number m equation, as in Mary, third coefficient, plus ... all the way up to the mth equation, m as in Mary, and the nth, n as in Nancy, variable, so amn xn, and we're looking at number b, or number m as in Mary, it's the mth equation, b value. This is the most general system of m equations and unknowns. Now we're going to develop in this section a couple of really important methods for solving the general system of equations, and they're computer methods. They're completely applicable to technology, using technology. But we need some terminology first. We need a lot of, not that much. We need some terminology before we can dig into this. So let's do that. Let's look at some important terminology. Important terminology. In other words, vocabulary. Okay. So let's take a look at our first bit of terminology. So I'd like you to consider with me, consider a system. Consider the system of equations, real short system, real small system, x minus y equals 4, and 2x plus y equals 2. Okay, we learned real early on in our math career in elementary algebra that if we were to graph this system, we would be looking at what? Do you remember? Kind of important. We'd be looking at two lines. In fact, this system represents two lines. This system represents two lines in R2 in the xy plane. if you've had Calc 3, this is that R2 is called two space, two lines in R2. These lines intersect. Okay, I'm going to take my word for it for now. These lines intersect. These lines intersect. And they intersect at the point 2, -2. In other words, each of these equations is satisfied for x equals 2 and y equals -2, and geometrically this represents two lines that intersect only at one point. Lines can intersect at more than one point. We'll talk about that in a minute. The solution to the system is x equals 2, y equals -2. And here's our first bit of vocabulary for our course. This is not new. This is the terminology you've seen before. The system is said to be consistent. And that's our first bit of terminology for right now. Consistent. Okay. So for us, this pair of lines intersecting at a point, or even better, the fact that this system of equations has a solution means that this system is called consistent. Okay, so consistent systems have a solution. Okay. So does that mean that a consistent system can only have one solution? Well, let's talk about that. So now consider the new system. And I'm going to leave the first equation alone from this previous system. I'm going to recycle that equation. But the second equation, instead of 2x plus y equals 2, is now 2x minus 2y equals 8. Okay. Again, each of these equations represents a line. Now notice the second line, 2x minus 2y equals 8. If you multiply both sides by 1/2, you get the first equation. So this represents two lines that are right on top of each other. In other words, they represent the same line. So every point on either line, they're both the same line, is a solution. So as long as x minus y equals 4, 2x minus 2y is going to equal 8. So we're going to have an infinite number of solutions. And the solutions can be regarded as all the points on either line, the common line. The solution to the system can be written in a few different ways. Can be written as, well, the first equation is really all that's necessary to write this solution to this thing. So if you solve for x, you get x equals 4 plus y. And y, what's y equal to? Well, y equals any number. Okay, that's one way to write it. It's not too popular, although, I guess that's not true. That is kind of popular. Another way to do that is to introduce a new variable for y. See, y can be any number, any real number. Actually, any complex number also, I believe. Any number. Well, we're just going to stick with real numbers for right now. So we can write, instead of y equals y, we can write y equals t. If you've had Calc 3, then you see where I'm going with this. I formed a set of parametric equations. Even if you haven't had Calc 3, in pre-calc, a lot of instructors cover parametric equations. But and actually in Calc 2 we cover parametric equations. So a second way of doing this would be to write the x and y in terms of an additional variable, and It's often called a parameter in terms used in systems of equations. It's often called a free variable, but I'm not going to write that out for right now. The idea of a free variable. You could also write it as an ordered pair, 4 plus y, comma y. You could also write the solution in a way that you may not have seen yet. You can write it as in terms of one of those matrices, 4 plus y and y, in this sort of 2 rows and 1 column matrix. Okay, and we'll see the solutions written in all 4 ways in our course. Okay, by the way, back to terminology. So this system also has a solution. It happens to have an infinite number of them. Okay, this system is also called consistent. This system is also called consistent. Okay, this system is also called consistent. Consistent. So if a system has at least one solution, then it's called consistent. Okay, so consistent systems have at least one solution. So in terms of systems of lines, to be consistent means that the lines intersect at one point, or they intersect everywhere. If the system of lines, the two lines has each of the lines has the same slope, then you're going to have an infinite number of solutions. Okay? If they have different slopes, then obviously we're going to have one solution. Okay. Okay. Let's take a look at another bit of terminology for our course. Next, consider another system. Next, consider the system. And what we're going to do with this system, let's consider the system, still the same equation, x minus y equals 4. But the second equation is now x minus y equals 3. Okay. So without even looking at these equations as representing lines, it's immediately apparent to us that this system has no solutions. Think about it for a minute. The first equation, it says subtract 2 numbers and get 4. There are an infinite number of ways we can subtract 2 numbers and get 4. 5 minus 1, 6 minus 4. I'm sorry, 6 minus 2, sorry, etc., etc., etc. There are many ways we can subtract 2 numbers and get 4. However, can you subtract those same 2 numbers and also get 3? No, it's impossible for this system to have a solution. X minus y equals 4, and at the same time x minus y is 3. No, numbers don't work that way. In terms of graphing, considering these system as representing lines, they represent 2 different lines, but the lines have the same slope. They both have a slope of 1. Okay, so these lines are parallel lines. So there's no intersection. So can parallel lines intersect? Sure, as long as they're the same line, as long as the equations represent the same line. However, if the lines are not the same lines and they have the same slope, they're not going to intersect, obviously. So this system has no solution. This system has no solution. And the system is called inconsistent. The system is called inconsistent. Okay, that's a lot of example just to get 2 words, but they're important words. So it's called inconsistent. So inconsistent systems have no solution. Okay, and those are the 2 words for the moment. So consistent systems, consistent systems. They have one solution, or infinitely many solutions. Infinitely many solutions. And inconsistent systems have no solution. So inconsistent systems. Oops. Inconsistent. I'm having a hard time spelling consistent. Inconsistent systems have no solution. No solutions. Okay. Okay. So now let's get down to methods. Let's get down to methods of solving systems of equations. This first method is extremely popular in mathematics for sciences, mathematics for STEM majors. It's called the Gauss-Jordan elimination method. This method is very easily applicable to using technology and uses these objects that I've sort of alluded to called matrices. The idea is to transform a system of equations into a simpler system of equations somehow that has the solution easily identifiable. So the idea is to perform certain operations, very, very specific operations, certain operations to transform a system of equations, to transform a system of equations into an equivalent system. Equivalent system meaning having the same solution as the original system, equivalent system. And just using three variables, say x, y, and z, the idea would be to transform the system of, let's say, three equations and three unknowns into x equals some number, put star, y equals some number, and z equals some number. Okay, that's kind of a very simple system. If you have x equals 5, y equals 3, and z equals -1, it's kind of easy to read the solution right off that system. Okay. Now, in order to do this, we have, or to describe the Gauss-Jordan elimination method, we have three allowable operations, only three, and we can't make up new operations. Okay, so we have three allowable operations. The first allowable operation is that we can interchange two equations. This is kind of a no-brainer, that it's okay. We can interchange two equations. If I rewrite a system of three equations by interchanging the first and third equation, I have the same three equations, just in different order. Okay, so I can interchange any two equations. Okay. The second is that I can multiply both sides of an equation by a non-zero number, and this is often abbreviated. I can multiply an equation, which seems kind of weird to say multiply an equation, but it really means multiply both sides of an equation. I can multiply an equation by a non-zero number. Pretty clear that that's not going to change the solution to equation. If you multiply both sides of an equation by a non-zero number, you don't change the solution to the equation. We learn that in elementary algebra. The third allowable operation is a little more complicated sounding. The third operation says that we can replace an equation, replace any particular equation. Replace an equation by itself plus a multiple of another equation. It's okay, so we can replace an equation by itself plus a multiple of another equation. I'm going to use some notation that's not used in our textbook to help us write these three allowable operations out a little more simply. Okay, so off to the left here in green, I'm going to write out using some notation that's used in other textbooks, just not our textbook. Okay, you're free to use this notation. Let's say we use the capital letter E for equation. E means equation. So we can interchange two equations. We could take equation I, so E sub I, and double arrow means interchange it with, switch it with equation J. Okay. So number two, we can multiply an equation by whatever we want, except for 0. So we can take an equation I, could be equation 1, equation 2, etc., 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 and we can multiply by a non-zero number A and put it back into the position of equation I. Okay. So what will the third one look like, the third operation look like? The third operation is to replace an equation by itself, E sub I, plus a multiple, let's say B, of some other equation times equation J, and then put that back into equation I. So the arrow equation I means we're replacing equation I with itself, E sub I, equation I plus some multiple of another equation, B times equation J. Something to note, and this is a very, very important note, very, very important note. This is this idea that I'm going to present to you now is probably the most common use of these operations. 2 and 3 can be combined to a single operation. 2 and 3 can be, and often is, it's an understatement to say it just can be combined to a single, take A times row I, or equation I, plus B times equation J, and put it back into the position of equation I. Okay. This is probably the operation we will use the most. Okay. So let's see how this works. Remember, the idea with the Gauss-Jordan elimination method is to somehow get x, y, and z in this sort of diagonal arrangement of variables to reveal the solution to us. Let's apply this. Let's solve a system. So let's solve the system that I've written out for us with the variables x, y, and z. Remember that the idea is to end up with x equals, y equals, and z equals somehow. To eliminate, or to eliminate two variables from each equation so that we can somehow simply identify x, y, and z. So it's pretty clear that the system's not already in that form. Notice that a couple things wrong with the x. The x, the first variable. First of all, it has a coefficient of 3, and we need it to be x just by itself. And the second, it has x's beneath it. So what I'm going to do is I'm going to use that third operation. I'm going to use a times equation I plus b times equation j and put it back into the position of equation I. And I'm going to use that for equations 2 and 3. I'm going to get rid of the x's below the 3x. Okay, so the first thing I'm going to do is first thing I'm not going to do is I'm not going to do anything with the first equation. So I'm going to have 3x plus y minus 2z equals 3. And I want to get rid of the x. The x is below 3x. So what I'm going to do is I'm going to take 3 times the second equation. So 3 times e2. That'll give me 3x in the position of x in the second equation. And I'm going to subtract the first equation, e1. So 3 multiplied by the second equation gives me 3x. And if I subtract the 3x in the first equation, I get 0. And I'm going to put that in the position of e2. So I'm going to take 3 times the second equation and subtract the first. So 3 times x is 3x minus 3x is 0. Now I have to do the same thing with the y's and the z's and the constant side. So I'm going to take 3 times negative 8y is negative 24y and subtract y, so that gives me negative 25y. So minus 25y. Feel free to stop the video anytime to confirm this with yourself. Okay. 3 times equation 2 minus equation 1. So now the z's. 3 times negative 4z is negative 12z. Take away 2. Take away negative 2 will give us negative 10. And finally, 3 times negative 4 would give us negative 12. Take away 3 is negative 15. And look at how painfully slow and complicated that was to get that line. This method is not a method that's designed for humans to do necessarily. It's a method that's very, very easily applied for a computer. A computer does this very, 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 very quickly. Okay. For the time being, though, we need to do this by hand so we get an idea of what's going on. So it brings up a good question on your homework and on exams. Should you be prepared to do this by hand? And the answer is yes. Yes, I may have you solve a system by hand using this technique. But for the most part, you can use your graphing calculators and whatnot to do this. Okay. I'm not going to have you solving systems of 5 equations and 5 unknowns using this technique. It really doesn't measure what you know, or that you know what's going on to do a system that large. But you should be able to do a small system by hand. Okay, so let's continue this this process. I want to get rid of the x in the third equation, so I'm going to do the same thing. I'm going to take 3 times equation 3 and subtract equation 1, and then put it back in the position of equation 3. 3 times equation 3, subtract equation 1, and then put it back in the position of equation 3. Okay, so I'm going to do this fairly quickly so that things move along, and you could verify the arithmetic here. So if I take 3 times x and then minus 3x, I get 0. If I take 3 times 2 is 6 and subtract 3 times 2y is 6y and subtract 1y, I get 5y. If I do the same thing with the z, I get negative 4z. Again, you can confirm this, and maybe you should, just to make sure that you understand what's going on. With the constant term, I'm going to get 3 times 1 is 3 minus 3 is 0. And that's our start. That's the start to this. The next part of the procedure is to do the same thing with the second equation in the system we have on the right. That is, get the negative 25y to stay there and get rid of the y's above and below it. Okay, so what I'm going to do is I'm going to leave the second equation alone in the system on the right. I'm going to leave it as negative 25y, take away 10z equals negative 15. Then I'm going to use that third operation to eliminate the y in the first equation and third equation. Okay, so how am I going to do that? Well, focus right now. Focus right this minute on the system on the left. Oh, sorry, the system on the right. And I'm going to I'm going to isolate something here, and I'm going to change its color, let's say to green. Focus on that plus y and the minus 25y. I want the minus 25y to stick around, but I want the plus y to vanish using that third operation. So I'm going to do something. First, I'm going to do something to equation 1. I'm going to multiply equation 1 by what? If you thought or said 25, cool. I'm going to multiply equation 1 by 25, and I'm going to add equation 2 to it and put it back into the position of equation 1. Okay, so I'm going to take 25 times equation 1, and I'm going to add equation 2 and put that back into the position of equation 1. If I do that, I'm not going to be adding any y terms to the first equation, but I am multiplying the first equation by 25. So 25 times 3 is, oops, I want to do this in black. So 25 times 3 is 75x. 0y, the y's cancel out. And you should verify the arithmetic. I'm going to get minus 60z, and I'm going to get 60. Okay, let's move this along. I want to now eliminate in the third equation the 5y. So give me a second here. First change it back to the original colors. And focus now on, I'm highlighting in green, the terms negative 25y and 5y. I want that 5y to be 0. So I'm going to do the same thing I did, same type of thing I did just a few seconds ago. I'm going to take this third equation and multiply by 5 and add the second equation to that, and then put that back into the position of the third equation. Okay. So in terms of writing out the operation, I'm going to take 5 times equation 3, 5 times equation 3, plus equation 2, and put it back in the position of equation 3. Okay, so let's do that. All right, if I do that, I'm going to have 5 times y is 5y, minus 25y, plus negative 25y is 0, so that's nice. And I'm going to get negative 30z. If I do that with the z terms, if I take 5 times negative 4z, I get negative 20z, and then add the negative 10z, I get negative 30z, and equals negative 15. Okay, so again, painfully slow and tedious for humans to do, but computers do this very, very, very quickly. Finally, let's get that negative 30z to be by itself with no z terms above it. So the operations are going to be to get rid of the negative 60z. Get rid of the negative 60z. I'm going to take equation 1, and I'm going to add how many equation 3's? Negative 60 plus what times negative 30 is 0. I'm going to take equation 1 and subtract 2 equation 3's. I'm going to take equation 1 and subtract 2 equation 3's and put it back into the position of equation 1. Okay, if I do that, I'm going to get 75x equals 90. So what am I going to do to get rid of the negative 10z? To get rid of the negative 10z, I'm going to take 3 equation 2's. That'll give me negative 30z. And I'm going to subtract equation 3, so it'll be plus 30z, will give 0. So I'm going to take, in the second equation, I'm going to take 3 equation 3's. Again, stop the video anytime you need to verify this with yourself. 3 equation 3's, 3 equation 2's. 3 equation 2's. And I'm going to subtract equation 3. I'm going to put that back into the position of equation 2. That's going to get rid of the z. It's also going to keep me with the negative 75y. Why does that become negative 75? Because negative 25y, negative 25 times 3 is negative 75. And that leaves me with negative 30. And I'm not doing anything with the third equation. Negative 30z equals negative 15. Looks like we're almost there. Looks like we almost have that x, y, z on the left-hand side in sort of the diagonal form equals constants on the right-hand side. The only thing we need to do is get those coefficients to be 1. And to do that, I'm going to use the second operation. It says I can multiply any row, any equation by a non-zero number. Okay. So I'm going to do that very quickly here. Okay. In practice by hand, this doesn't speed up any, but in practice on a computer or on a calculator, this is almost instant. So we're going to get some relief soon with this, okay? Okay. All right. So what I'm going to do is I'm going to multiply the first equation by 1 over 75, the second equation by negative 1 over 75, and the third equation by negative 1 over 30. To get those coefficients to be 1, the coefficients of x, y, and z to be 1. So I'm going to multiply the first equation by 1/75. I'm going to take the second equation and multiply it by negative 1/75. I'm going to take the third equation and multiply it by negative 1/30. And that's going to give me the solution. I'm going to get x equals 90 divided by 75 is 1.2. Negative 30 times negative 1 over 75 is 0.4. And negative 1 over 30 times negative 15, it's a half. And there's our solution. X equals 1.2, y equals 0.4, z equals 0.5. This is an example of an application of the Gauss-Jordan elimination method. But we're going to polish it up a whole lot. Notice that in the application of this method that we really don't need to write the variables. We really don't need to write the variables. For example, in the first equation on the right, after the initial system written down, instead of writing 3x plus y minus 2z equals 3, we can simply write a row of numbers in the same order: 3, 1, negative 2, and 3. We don't need to see the variables here. As long as we keep the variables in the positions of the first column, second column, and third column to represent x, y, and z, we really don't need to see the variables. Sort of like in pre-calc when you studied synthetic division, we didn't need to see the powers in the polynomial, because if they're kept in the same position, then we just assume that the numbers represent coefficients of those powers. Okay. So we're going to replace those three operations that we do with equations with three operations that we do simply with rows of numbers. Rows go from left to right. And they're exactly the same operations, They're just going to be involving rows rather than equations. Okay, those operations are called elementary row operations. Elementary row operations. These elementary row operations, which I've written out behind the scenes for us, are exactly the same operations that we had with equations. And notice I've replaced the E for equations with, what do you think the R's, capital R's are? They're rows. There is no change whatsoever. And you'll see how this really makes for something that's a little easier on the eyes when we're applying the Gauss-Jordan elimination method. Right, just as before, note that 2 and 3 can be combined. 2 and 3 can be, and very, very often are, can be, most of the time are actually, combined to A times row I plus B times row J. Put that back into the row I that is being manipulated. Okay. Now let's revisit. It's a little tedious. In fact, it's a lot tedious, but let's revisit that last system we just looked at. But let's eliminate all the variables, and let's use matrices. Let's use these rectangular arrays of numbers to solve the system. So here's the same system. In fact, I just cut it and pasted from a few minutes ago. Here's the same system. So the first thing I want to do is I want to get rid of all the x's, the y's, and the z's. Okay. The first thing I want to do is write out a matrix for the system. While I'm doing that, here's a self-test for you. What did we call that matrix again? I gave it a name. I gave this matrix a name. What did I call it? I called it the Augmented Matrix. Augmented Matrix. It's not so important that you get that name right away, but eventually it's a good idea for you to understand that this is called the Augmented Matrix. Look what I'm doing. I'm eliminating all the variables, but I'm keeping the position of the coefficients in distinct columns. I'm not moving them around, I'm keeping them in the same exact position. I'm putting a little dotted line here. This is optional. Some textbooks put it in, some textbooks don't. And I put it in. I like to because it reminds me of the separation between the coefficients of the variables and the constant terms in the system. Okay. So what's the idea? Well, the idea, remember, is to have x, y, and z isolated. The idea is to produce another matrix that looks like this. It looks like x equals something. So 1x equals something. 1y equals something. And 1z equals something. Well, this is an augmented matrix. We need numbers everywhere. So what should the coefficients of everything else be? Well, zeros. The idea is to somehow, if possible, and we're going to find that out soon. It's not always possible to get this final augmented matrix to look like this. But the idea is to get a matrix that looks like this, and we can read the solution. Since we're keeping track of what columns belong to what variables, this says x equals for the first row, and y equals for the one in the second row in the second column, and z equals for the third row and third column, the number. Okay, so let's do this. Let's do that. Let's focus on the x variable. Let's try to get 1 in the upper left position and zeros below that. So how did I do that in the previous example? I kept the 3 there and made 1s below the 3. Okay, so I'm going to do that exact same thing right now. But it's so much easier to do this without having to keep track of the variables, to keep writing the variables over and over and over again. I want 0 below that 3. I want both those zeros below that 3 in the upper left. So I'm going to take 3 times row 2, and I'm going to subtract row 1. Isn't that easier to see? 3 times 1 is 3, minus 3 is 0. To do the same thing with the third row, I'm going to take 3 times row 3, and I'm going to subtract row 1. And that should get us in a nice position. So I'm not going to do anything with the first row. 3, 1, negative 2, 3. Okay. Now, I take 3 times row 2 minus row 1. I'm going to start a little slow, and then I'm going to move this along a little more quickly. So focus on this operation. 3 times row 2 minus row 1. 3 times 1 is 3, minus 3 is 0. 3 times, now the second entry in the second row. 3 times negative 8 is negative 24. Take away 1 is negative 25. 3 times negative 4 is negative 12. Take away negative 2 is what? Negative 10. 3 times negative 4 in that last column. 3 times negative 4 is negative 12. Take away 3 more is negative 15. So see how that works? Third row. 3 times row 3 minus row 1. 3 times 1 is 3, minus 3 is 0. Second entry in the third row. 3 times 2 is 6, minus the 1 in row 1 is 5. 3 times negative 2 is negative 6. Take away negative 2 is negative 4. And finally, 3 times 1 is 3, minus 3 is 0. Don't have to look at the variables at all. This is kind of nice. Okay, so let's move this along. I would like to isolate y. That means in the second row, in the second column, that negative 25, I'd like it to be 1, and I'd like to have zeros above and below it. So I can identify the coefficient of y as 1, and the coefficients of y above and below it to be 0. Okay, so what I'm going to do is I'm not going to mess with the second row. I'm not going to do anything with the second row. Yet. I will eventually, because I want that coefficient to be 1. But I want that 1 that's above negative 25 to be 0. So what am I going to do? What elementary row operation am I going to do? I'm going to take 25 times row 1. And I'm going to add row 2. And put it back into the position of row 1. Okay, now this is where I'm going to move things along a little bit, so you can stop the video as we move along to verify the numbers here if you'd like. In fact, I think it's probably a good idea at first. But I'm going to get 75, and I multiply 25 times 3 to get 75. I'm going to get 0, that was the whole idea. I'm going to get negative 60. I'm going to get 60. I want to get that entry below negative 25, that 5, I need it to be 0. So I'm going to take 5 row 3s, and I'm going to add 1 row 2. 5 times 5 is 25, minus 25 is 0, and the result is I'm going to get 0. I'm going to get the 0 that I wanted, that was the whole idea, negative 30, and negative 15. Okay, what's the next step? I see that negative 30 in the third row, I'd like to get it to be by itself in terms, or specifically, what I mean by that is I'd like to have that remain, and I'd like zeros to appear above it. Okay. So the elementary row operations I'm going to do, let's say on the first row. In the first row, how am I going to get that negative 60 to not be there by using row 3 to get rid of it? Row 3 and the combined operation, the operations 2 and 3. Well, I'm going to take row 1. I'm going to be operating on row 1. And I'm going to subtract 2 row 3s. Negative 60 is in row 1. Minus 2 times negative 30, that's 0. Okay. Now how am I going to get rid of that negative 10 above the negative 30? I'm going to do a similar thing. I'm going to take, let's see, what am I going to do? I'm going to take 3 row 2s. 3 row 2s. And that will give me, in the position of that negative 10, it'll be negative 30. Then I'm going to subtract row 3. Let's do these operations. elementary row operations. The first one, row 1 take away 2, row 3. Row 1 take away 2, row 3 leaves me with 75, 0, 0 that I wanted, and what's going to appear in that last position in the first row? Row 1 minus 2, row 3. Row 1, 60, minus 2 times negative 15. Well, that's going to be 90. 3 row 2 minus row 3. No effect there. No effect for the negative 25. 3 row 2. 3 row 2. 3 times negative 10 minus negative 30. That means plus 30. That's 0. That's what I wanted. And the 3 row 2 minus row 3. 3 times negative 15 is negative 45. Take away negative 15, so really plus 15 is negative 30. This is what a computer is doing very, 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 very quickly. Very quickly. Finally, I want the coefficients of x, y, and z to be 1. Can't always do it. Okay, we'll see that real soon. We can't always do it, but here we can. This is the same system as we did earlier. So to finish things off, I'm going to take 1/75th of row 1. I'm going to take negative 1/25th of row 2, and I'm going to take negative 1/30th of row 3, and that will allow me to isolate the x, the y, and the z. I'm going to get x is 1.2. Oops, I'm going to get y, so 0, 1 is the coefficient of y, 0 is the coefficient of z equals 0.4. I get 0 for coefficient x, 0 for coefficient of y, 1 for coefficient of z equals 0.5. Our final step is to then write the solution as x equals 1.2, y equals 0.4, z equals 0.5. So this is the Gauss-Jordan elimination method in action, okay? The problem is, and it's kind of a big problem, but it's not one we can't get around. The problem is, it isn't always possible to get that nice final matrix. Here, I'll write this out, problem. It isn't always possible. Isn't always possible. Oops. To obtain this matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, something, something, something. It's not always possible to get this. What we have to do is we have to try to get it to, as much as possible, this form. We want to make it as much as possible this form. As much as possible of this form has a special name. It's called reduced row echelon form. It's called reduced row echelon form. The optimum form would be the one I just wrote above these words. But it's not always possible to get that nice form, optimum form of reduced row echelon form. We're going to abbreviate this as RREF. RREF means reduced row echelon form. So, what is reduced row echelon form? Well, you're looking at the best possible outcome. The best possible outcome would be that we have this these diagonals, this nice straight line diagonal of 1s, 0s everywhere else except for the constant column. Okay, but that's the special case of the nice case of RREF. So what is the RREF? Well, RREF from page 7 in your textbook satisfies 4 requirements. Let's take a look at those 4 requirements. So here are the 4 things. 1. Any row of zeros, which are called zero rows, any row of zeros appear at the bottom. Any row of zeros appear at the bottom. It's the bottom row. So above, in that optimum case, that real nice case, we have no 0 rows, but we could have 0 rows if we had, suppose we had 4 equations, but only 3 unknowns. Obviously, we're not going to have just 3 rows, then we'll have 4 rows. So it's possible to have additional rows. So any 0 rows appear at the bottom. Okay. 2. What would we like the first non-zero entry be in a row? Well, pretty clear that the optimum case has 1 there. So the first non-zero entry, the first non-zero entry in a row, in a non-zero row is 1. Okay, that 1 has a special name. That 1 is called a leading 1. It's called a leading 1. Okay, for our optimum case, the leading 1s give us the coefficients of the x, y, and z, etc. Okay, so how do we get that diagonal pattern in words? Okay, it's sort of like the leading 1s are in a diagonal. Well, that's not the wording that's used here. So it does start with the leading 1. The leading 1 of a non-zero row, my writing is getting pretty bad here, non-zero row appears to the right. Not period. That made it sound like that's the end of the sentence. Appears to the right. To the right what? To the right of the leading 1 of the previous of any previous row. The leading 1 of any non-zero row, okay, appears to the right of the leading 1. The leading 1 of any preceding row. Any preceding row. Okay. That's not quite enough. It's not quite enough. We need to get those zeros. We need to get those zeros above and below all the leading 1s. Okay. And we do that by number 4. All other entries of a column containing a leading 1, are 0. Now columns, remember, they're up and down. Okay, rows go left to right, columns go up and down. So if you have a leading 1, all the other entries of a column that contains that leading 1 be 0. That means we have 1s above and below leading 0s. So here's a quick example to make sure that you're okay with RREF. So determine whether, for example, determine whether the matrix is in RREF. reduced row echelon form. Part A. Part A, the matrix 1, 0, 4, 0, 0, 1. Okay. Well, you've probably, your eye probably focused on one number in there that really destroyed things. But go through the four things, or try to figure out which of the four things is violated. So the first thing is any row of zeros appear at the bottom. That's true. Well, how can it be true? Well, there are no zero rows to violate it. If you can't violate something, it's automatically true. So, are all zero rows at the bottom? Yeah. Well, again, some students will say, or some people will say, well, there are no non-zero rows, so how can you put them at the bottom? Well, then I would counter with, is then one violated? Are there any non-zero rows that are not at the bottom? And the answer is no, so it's automatically satisfied. Okay, 2. The first non-zero entry in a non-zero row is 1. Are the first non-zero entries as we go from left to right 1? Yeah. 1 in the first row, 1 in the second row. So 3. The leading one of a non-zero row appears to the right of the leading one of previous rows. Yes. We really can't apply that to row number 1, but look at row number 2. Row number 2, the leading one appears to the right of the leading one in the previous row. They don't have to, the leading ones don't have to be in that nice straight line diagonal. Okay, so 4. Here's where we have a violation. All other entries of a column, not a row, but a column containing a leading one are 0. And that's, now this is number 4 is violated. Number 4 is violated. So the answer is not. The matrix is not in reduced row echelon form. The matrix is not in reduced row echelon form. So let's take a look at another one. B. Okay. This matrix is kind of big. Not that big. It's bigger than before. 1, 0, 0, 3, first row. Second row, 0, 0, 1, 5, third row, 0, 0, 0, 0, fourth row, 0, 0, 0, 0. Is this in reduced row echelon form? Are any rows of zeros appearing at the bottom of this matrix? Yes. The last 2 rows are zeros, they're at the bottom of the matrix. 2. The first non-zero entry in a non-zero row is 1. Yes. Yes. 1 is the first non-zero entry in the first row, 1 is the first non-zero entry in the second row. 3. The sort of diagonal behavior of the ones. Are the leading ones in a non-zero row to the right of the leading one of previous rows? Yes, the leading one in the second row is below and to the right of the first leading the leading one in the first row. Sure. So this is yes. This is RREF is in row reduced echelon form. Let's take a look at another one. Some of these can be tricky. C. 1, -3, 0, 5, 7. Just a matrix with 1 row and 5 columns. Is this in row reduced echelon form? The answer is yes. All the rows of zeros are at the bottom. Yeah, that's not, you can't violate it, so it's true. The first non-zero entry is 1. Yep. Leading ones form that diagonal procession. Yeah, there are no other leading ones other than the first row, so it's automatically satisfied. If it's not satisfied, you have to be able to come up with something that makes it not satisfied. So again, number 3, the leading one of a non-zero row appears to the right of the leading ones of any previous row, where there are no previous rows. There's only 1 row, so you can't violate it. You can't violate number 3. Okay. Are all the entries of a column containing a leading 1, 0? Are all the entries of the first column 0 above and below? Well, there aren't any entries above and below the first entry, so you can't violate it, so it's true. This is in RREF. So logic can be tricky. This is RREF. Okay. Okay, so I think you get the idea of RREF. Let's solve another system using this Gauss-Jordan elimination method by trying to produce the reduced row echelon form. By the way, that is the Gauss-Jordan elimination method. It is to write the augmented matrix and use the elementary row operations to produce the RREF. So you might think then, does RREF always exist? Yes, RREF always exists, no matter what, it always exists. So we can always use the Gauss-Jordan elimination method. Let's do it. Let's do an example. Fudge. So here's our system, solved by the Gauss-Jordan elimination method. First step, write out the augmented matrix for the system. 1, 0, 2, 0, 1, 1, 1, negative 1, 1, 1, negative 1, 2. Dotted line to separate the coefficients of the variables with the constant numbers, the constants for the system. Okay. So remember, the idea is to try to get the reduced row echelon form for this matrix. Well, I'd like to get that x equals, that coefficient of 1 in the upper left to be alone. I'd like to get that 2 below that leading 1 in the first row. I'd like to get that 2 in that column to be 0 in the first column. Okay. So can you think of the elementary row operation? I'm going to take row 3, third row, and I'm going to subtract 2 row 1s. And that's the only operation I'm going to do for the first step here. Okay. So I'm not going to do anything with the first row. I'm not going to do anything with the second row. And I'm going to get that 0 in the third row, the first entry. So row 3, 2 minus 2 times row 1. 2 times 1 is 2, so 2 minus 2 is 0. And you can pause the video if you want to try this yourself to get the other entries. If you do that, you should get 0, 1, negative 1, and 0. And I strongly encourage you to do that. Strongly encourage you to do that. All right. Okay, so what's our next step? Well, I'm now focusing on the second row, the position of the y variable. That it has a coefficient of 1. That's really nice. So I'm not going to do anything with that row. 0, 1, negative 1, negative 1. And I'd like to have zeros above and below that leading 1. Well, in the first row, I already have that happening. So how am I going to get that 0 beneath that leading 1 in the second row in the second column? Very simple. I'm going to take row 3. I'm going to subtract row 2 and put it back into the position of row 3. Okay, if I do that, I get 0, 0, 0, and 1. Oh, there goes that nice straight line diagonal of 1s. There's no way we're going to get that. There's no way to get that. So is this RREF? Is this RREF? Well, remember the 4 things that have to be satisfied. Well, we don't have any rows of zeros to worry about. The first non-zero entry is 1 in each row, of course. 1, 1, 1, 1 first row, 1 in the second row, 1 sort of skipped over in the third row, but it's still a 1. Leading 1s appear to the right of leading ones in previous rows? Of course, that's satisfied. Problem is number 4, all other entries in a column containing a leading one are not 0 in that 4th column, in that last column. So we have one more operation to do to produce the RREF. One more set of operations, I guess. So the third row is fine. Okay. So the operation, or the elementary row operations, in order to get 0 in that entry, in the last entry in the first row, I'm going to take the first row and I'm going to subtract the third row. That will give me my 0 in that position. I need that. It'll also give me 1, and you again stop the video if you want to try to get this on your own. It might be a good idea, although you're going to get homework to do it also. So, okay. But I think it might be a good idea for you to stop the video and see if you can anticipate the correct answers and stuff. Okay, I need to get that -1 out of there. I need to transform it to 0, and to do that, I am going to take row 2. It's always the first row, the first thing, you always involve the row that you're operating on first in this operation. So I'm going to take row 2, and I'm going to add row 3. I'm going to put it back in the position of row 2. If I do that, I get 0, 1, -1, and 0. And this is in reduced row echelon form. Now, I want to transform this back into a system of equations. So the system of equations then looks like 1x1 plus 0x2 plus 1x3, so x1 plus x3. I'm transforming this final augmented matrix back into a system. I'm going to get 0x1, 1x2 minus x3 equals 0. What about that last row? You can think about that last row as representing the coefficients of x1, x2, and x3. If I just include the x3, it's saying 0x3 equals 1. That's impossible. There is no number that you could, x3, that you can multiply by 0 and get 1. This is impossible. This is completely impossible. Impossible. So the conclusion is that the system has no solution. The conclusion is the system has no solution. The system is what? Well, let me give you a hint. It's not consistent. The system is inconsistent, using the terminology we talked about 45 minutes ago or an hour ago. Inconsistent. Okay. So, you've probably been thinking, how can I do this with a calculator? If you're thinking that, that's a good place for you to be right now. Calculators are very easy to use. The Texas Instruments in particular are very easy to use to perform the operations in the Gauss-Jordan elimination method. The first thing to do is to enter the actual matrix into the graphing calculator. Again, I'm going to use the TI-84, and I'll describe this. If you already know how to do this, you can skip forward in the video to our next example. But to use the Gauss-Jordan elimination method, first thing we do is we enter the matrix. So if you turn your calculator on and you push second matrix, second matrix, or what is it, second x to the minus 1. If you push second x to the minus 1, you see a whole list of matrices available to us, 1 through 7, and I think I can scroll down further. Along the top row, you see names, math, and edit. You get the cursor over edit. You push the right button, the cursor to the right, edit, and you see then the calculator is highlighted number 1. And unless you want to edit matrix 2, 3, or 4, push enter. And at this point, it's waiting for you to enter the dimensions of the matrix, the number of rows by the number of columns. Rows go across, columns go up and down. So our particular matrix, and let's do this for the example we just did. The example we just did, our augmented matrix has 3 rows and how many columns? 3 rows and 4 columns. So enter 3 and 4 for the number of rows and columns. As soon as you enter that, the number of columns 4, you push enter, and you see that the cursor is now highlighted over the entry in the first row in the first column, and you just start entering putting in the entries, inputting the entries, and you move from one entry to the next by pushing enter, and the calculator enters the entries from left to right. So literally, you push, in the first row we have 1, 0, 1, 1. You push 1, enter, 0, enter, push enter, then 1, push enter, then 1, push enter. Now it's waiting for the entries in the second row. You push 0, enter, 1, see 0, enter, 1, enter, -1, enter, and -1, and then push enter. Then you enter the third row. You push enter again after that last entry of -1. You push 2, enter 1, enter 1, enter, and 2, enter. 2, enter. At this point, you've entered the matrix. For the matrix A, our augmented matrix. Then push second mode or second quit. It's actually mode, and above the mode is quit. All right. Then you perform the reduced row operation. You produce the elementary row operations to get the reduced row echelon form. The calculator is programmed for this. So to get the reduced row echelon form using the calculator now, push second matrix again, second matrix, and we want to perform matrix arithmetic or matrix math. So get the cursor over math, M-A-T-H, and you notice that there's some things there. There's DET for determinant and other things. And if you scroll past 7, all the way to 9, and then 0, and then they start using letters A, B. You notice that B is RREF. When you get the cursor over RREF, you push enter. Okay. At this point, you should see RREF with open parentheses. Then enter our matrix. Our matrix is A, so you would push second matrix 1. Second matrix. And our matrix is A, which is number 1, and close parentheses. 1, close parentheses, and push enter. And something amazing happens. I think it's amazing. We get the reduced row echelon form. The calculator produces RREF for us. Okay, and the RREF is unique. Every matrix has exactly one RREF. So there's no worrying about if you're going to get a different RREF for a particular system. Okay. Okay, so let's solve another problem. Let's solve another problem. Maybe we'll use the calculator to do this problem. So let me write out our next example. And here it is. Solved by the Gauss-Jordan elimination method, and the only change from the previous example is highlighted in red there. In the third equation, I've changed the constant from 2, I believe it was, to 1. Also, I've written out the augmented matrix with that corresponding change in the third row in the fourth column to be the red one. Now I'm going to use my calculator to do this. Okay, on your exam or exams where you do this, what you do to indicate that you used your calculator is you draw a little arrow and you write RREF. That would be enough, and you'd say you can even write calculator. Unless I ask you to do the row operations by hand, use your calculator, and the calculator will produce in the first column 1 0 0, and 0 1 0, second column, third column 1 negative 1 and 0, and final column 1 negative 1 and 0. And before we go too much further on this, if I ask you on an exam to do the example by hand, and you really want to tune in here if you're not listening. If I ask you to do something by hand, then you show those red operations right next to the matrix that I did previous. This is very important. You show the red operations so that I know what you did to get those entries. Okay. All right. So here's the reduced row echelon form for the Gauss-Jordan elimination method. This is as produced by the TI-84 calculator. Then write out the final system. The final system then looks like x1 plus x3 equals 1, x2 minus x3 equals negative 1, and 0x3 equals 0. Okay. We get another kind of strange thing, just like we did in the previous example. Previous example, we got our last equation to be 0x equals, I think it was 1, so we got no solution. But look at that last equation now. Look what's going on here. In the previous example, we got 0x3 equals 1. 0 times x3 equals 1 had no solution. In this, we have 0x3 equals 0. What is the solution to this equation? This has any x3, any value for x3 will work. Any value for x3 will work. Not only does this system have a solution, it has an infinite number of solutions. Okay, this system has an infinite number of solutions. Okay, so how do we write the solutions? Well, we have the system solutions that the Gauss-Jordan elimination reduced to. Solve for the variables. x1 then is 1 minus x3. x2 is equal to negative 1 plus x3. And x3 equals any number. Any real number, or any number. Okay, so this system is consistent. Not only is it consistent, it has an infinite number of solutions. Okay, so let's think about what this means geometrically. If you've had calculus 3, you know that each of these equations represents a plane. Equations, linear equations with three variables represent planes. And this is saying that we have three planes intersecting in something more than just one point. How can three planes intersect in something more than a point? Well, you can have all three planes intersecting in a line. Just think about it. You can take two pieces of paper and sort of smash them into each other at an angle, and you have the intersection would be a line. You could also take a third piece of paper at a different angle than those two planes, and pass it through so that that third plane also hits that line. You have this is what we're looking at geometrically. Okay. Well, the geometry of the solutions is not too important for us. So if you haven't had Calc 3, don't worry about it. But a little bit more terminology here. The x1 and the x2 are called dependent variables. They're called dependent variables. You can kind of see why. Their values depend on what we choose for x3. Okay? x3 is not a dependent variable. We're free to choose it to be whatever we want. It's called a free variable. Free variable. In Calc 3, we would call that the parameter. Calculus 3. So free variable. The dependent variables are those variables that correspond to the leading ones in RREF. They correspond to the leading ones in RREF. Now, if you look back at the original RREF, or rather the RREF, the leading ones occur in the, and I'm going to do this in green, in the column for x1 and for x2. The leading ones occur in the columns for x1 and x2. So that's an indication that the x1 and x2 are going to be the dependent variables. Our solutions will be x1 and x2 depend on the independent variables, or sorry, the free variables. And the free variable in this case is x3. Okay, so a little bit more terminology there. Okay, so to finish up our video segment, I want to focus on some very specific kinds of systems of equations. Very, very specific kinds of systems of equations. I want to focus on systems of equations where the constants in the system, the numbers on the right column of the system, are all zeros. Okay? The geometry of these systems of equations where you have the constants in the system are zero is that they represent lines in R2 or planes in R3 that pass through the origin. You notice that if the constants are all zero, then x1, x2, all the way up to xn equaling zero will work. Well, that corresponds to the origin. Okay? Such systems are called homogeneous systems, and they're very, very important in our work. Homogeneous systems of equations are where the constants are zero, and they can be viewed as planes or lines that pass through the origin, that contain the origin. Now, I want to ask an important question. This is an extremely important question I'd like you to think about. Question. What do all, no exceptions, all homogeneous systems have in common? And if you're thinking, well, they all pass through the origin, well, the equations do, but what do the systems have in common? What do the systems have in common? Well, if the homogeneous system represents planes and they all pass through the origin, that means the origin is always going to be a solution to each of the equations, which means that they're all consistent. All homogeneous systems are consistent. All homogeneous systems are consistent. Okay. The answer is they are all consistent. Okay. x1 equals x2 equals x3 equals all the way up to xn equaling 0 is always, just for homogeneous systems, always a solution. Okay? This solution is a very important one. This solution is called the trivial solution. Trivial solution. Okay, so all homogeneous systems, all systems of equations that have as their coefficients zeros on the right hand side of the system, they're all consistent and they all have the trivial solution. They all, since all the planes pass through the origin is going to be a solution. The only question is what about homogeneous systems? If they're always consistent, that means they're never inconsistent. They always have a solution. Then the only real question is, do they have infinite number of solutions? Remember, there are only 3 possibilities for systems. Consistent systems, which have two of the 3 possibilities. Either there's one solution for a consistent system or infinitely many, or for inconsistent systems you have no solutions. So the only question for homogeneous systems is whether or not there are solutions other than the trivial solution, the one the one where the values of all the variables are 0. Okay, let's take a look at a specific system, and we'll use our calculator to help us along with this. So I'm going to use the Gauss-Jordan elimination method to solve a homogeneous system. Remember, a homogeneous system is characterized by those constant terms, the constant numbers, the zeros as the constants for the system. I'm trying to highlight them so that they're in our lecture. So there. Those red zeros are what make a homogeneous system. And homogeneous systems always have the trivial solution. So I know this thing has a solution. In fact, I know I have a guaranteed solution of x1, x2, x3, x4, and x5 all equaling 0 are going to work. The question is, are there any others? So we set up the augmented matrix for the system, and I did that for us. Okay. And remember that we have 5 variables here. So the variables are x1, x2, x3, x4, and x5, with the constants being zeros again, homogeneous system. And I entered this into my graphing calculator to get an RREF as indicated. Okay. And again, most of the columns correspond to the variables. So x1, x2, x3, x4, x5. Interesting to note is that no matter what elementary row operations you use on a matrix that corresponds to a homogeneous system, that last column is never going to change. It's always going to be zeros. So back to our problem. What does this translate into? It translates into the system x1 minus 2x2 plus x5 equals 0. The second equation would be x3 equals 0. Then we have x4, just transforming the this final matrix into a final system, x4 minus x5 equals 0. Now remember, the leading ones correspond to the dependent variables. Those are the solutions, the variables that we get in terms of free variables. So the leading ones for our matrix are in the first row. I'll highlight it in 1. Second row, highlight it in 1. Highlight it in red maybe. That'll work. And the third row, highlight that in red. So that says that those variables x1, x3, and x4 are our dependent variables. So solving the first equation for our first dependent variable x1, that means x1 will equal 2x2 minus x5. x2, the second column doesn't contain a leading one, so x2 is a free variable. Free variable, so sorry. So x2 can equal any number. x3 is 0. x4 corresponds to a leading one equals x5. X4 is a dependent variable, so x4 equals x5. X5 is a free variable because the x5 did not correspond to a leading one. So x5 can be any number. Now x2 and x5, although they're any numbers, they can be any different numbers. They don't have to be the same numbers, and that's our solution. Okay, and I want to make sure you understand that this represents an infinite number of solutions. So let's just look at a specific solution. Let's say, just for the heck of it, let's pick a specific solution other than the trivial solution. They're all zeros. Let's pick a specific non-trivial solution. Well, I could do that. Oh, I can do it in an infinite number of ways. Let's say, let's let x2 equal 1 and x5 equal 3. Yeah. Let's do that. Why not? Let's let x2 equal 1, x5 equal 3. If we do that, we get the specific solution x1 equals 2x2, which is chosen to be 1, minus x5, 3. So x1 is negative 1. x2 is that 1 that we chose. x3 is 0. No choice for x3. x4 is x5, and x5 we chose to be 3, and x5 is 3. So one particular solution would be negative 1, 1, 0, 3, and 3. Okay. Most important things going on here are that homogeneous solutions are always consistent. They always have the trivial solution. This particular one was consistent, but also had non-trivial solutions, and one particular one we found, letting x2 equal 1, x5 equal 3. Okay, so let's take a look at a very important true or false question. This next theoretical question is going to follow us through the course. If a homogeneous system, true or false, if a homogeneous system, that means all the constants on the right are 0, or you can think about it as they represent planes that pass through the origin. If a homogeneous system has fewer equations than unknowns, then it has infinitely many solutions. This may seem like a really deep question, but it's not. So let's think about R3 and planes, just planes that we could visualize. if a homogeneous system has fewer equations, let's say each equation represents planes, so 2 planes, fewer equations, then unknowns, well, we have 3 variables, x, y, and z. We have 3 unknowns, but only 2 planes. The homogeneous system then must have true or false and infinitely many solutions. So we have 2 planes passing through the origin. The question is, do those 2 planes intersect in more than one place? Think about it. If you have 2 planes that pass through the origin, what is their intersection going to look like? Are they going to intersect first? Yes, because they're going to pass through the origin. But what is their intersection? What's the intersection then going to be of 2 planes? It's going to be a line. How many points are on the line? The answer is infinitely many points. So the answer is true. If a homogeneous system has fewer equations, there are fewer planes than they have unknown, then those 2 planes in this case are going to pass. They're going to intersect in a line, and a line contains an infinite number of points. Now, before we move on, the answer, of course, then is true. But if I remove the word homogeneous, then it's not true. If I have just any 2 planes, if I have a system with fewer equations, not homogeneous, but just any system with fewer equations than unknowns, if I have 2 planes that don't necessarily pass through the origin, those 2 planes don't have to intersect at all. So there would be maybe no solutions. Maybe they do intersect, in which case we would have an infinite number of solutions. If you got lost in this theory, the important thing is this particular true or false question. If you have 2 planes that pass through the origin, they must intersect in a line, which means they have infinitely many intersection points. The general statement then is, if a homogeneous system has fewer equations than unknowns, it has infinitely many solutions. This is true. Okay, this is actually a theorem in your textbook. This is theorem 1.1 on page 11. Okay. Okay, so to finish up, I want to look at one more method of solution, and don't panic. I know we've been at this for a couple hours now. I want to look at one more method of solution, and this method of solution is very similar to the Gauss-Jordan elimination method, except the row operations that are used to produce, or rather to remove one of the 4 things from that are required for the Gauss-Jordan RREF. Okay, if this didn't make sense, let's take a look at it. Again, the method is very easy to describe. We've done all the work we really need to do on Gauss-Jordan elimination method to get most of this next method. The Gauss-Jordan elimination method had 4 requirements for the reduced row echelon form, and number 4 said that all other entries of a column that contain a leading 1 are 0. That means we have zeros above and below the leading 1s. Removing number 4 allows for the entries above the leading 1s to be other than 0. Okay, so the last method, our second method for today, is called Gaussian elimination. Jordan has his name removed from this. It removes number 4 from RREF. So if you remove number 4 for RREF, you just get row echelon form. And row echelon form, REF, allows the entries above leading ones to be non-zero. Let's look at our last example for our video segment. Okay? So here's our last system. I want to use Gaussian elimination to solve the system. Okay, so there's our system, and I've taken the liberty to write out the augmented matrix. So Gaussian elimination and Gauss-Jordan elimination method, they both start out with the augmented matrix. But the difference starts to occur soon here. First, I want to get zeros below that 3. Okay, so I performed elementary row operations just like before to get those zeros. Next, I'd like to get zeros below negative 25, below the x2 variable coefficient negative 25, but I'm not going to bother with the number above negative 25. So the next step is to get 0 below the negative 25 by elementary row operations, but I'm not going to make zeros above negative 25. The next step then is to get zeros, actually the next step is not to get zeros anywhere. The next step is to not worry about what's above negative 30. If there were entries below negative 30, we would like them to be zeros, but we're not worrying about what's above leading ones. So the final step is to get leading ones. So we multiply the first row by 1/3. We multiply the second row by negative 1 over 25. We multiply the third row by negative 1 over 30. And we have not quite RREF. We have leading ones and zeros below the leading ones, but above the leading ones, it doesn't matter. Okay, so that's the Gauss-Jordan elimination method. Then the big difference. Then we transform into a final system of equations. The final system of equations then looks like 1x1 plus 1/3 x2 minus 2/3 x3 equals 1. And remember, this final matrix was called not reduced row echelon form, but just row echelon form, just a reminder. The second equation then is x2 plus 2/5 x3 equals 3/5. And x3 equals 1/2. Okay, well, this doesn't quite solve the system. To get the to get the solution, if we were using the Gauss-Jordan elimination method, we'd be done. We'd have x1, x2, and x3. But we don't have x1 and x2 here. We only know x3. So we use back substitution. We take the x3, the value of x3, and substitute it into the equation above it to find x2. So x2 then is 3/5 minus 2/5 x3. And that turns out to be, and I did this work off camera, this is 2/5. And to get x1, we back substitute the value for x3 and the value for x2 that we found just a second ago back into the first equation. So we find that x1 is then 1 minus 1/3 of x2, but x2 was 2/5, plus 2/3 of x3, which was 1/2. And again, I did the arithmetic off camera, and that tells us that x is a weird number. It's 18 over 15. So to end things with a couple comments, the Gauss-Jordan elimination method gives us zeros above and below the leading ones. The Gaussian elimination method, we take off the word Jordan from the method, has zeros below the leading ones, but above the leading ones we have not necessarily zero. And we use back substitution then to finish the problem. The final comment, and I'll end our video segment, is that the reduced row echelon form is unique. There's only one for a particular matrix. But REF, there are many different row echelon forms for a particular matrix. So if you get a different row echelon form than your classmates, that's okay, but there's only one reduced row echelon form. And that ends our video segment for a very long section, section 1.1. Go ahead and get started on homework when you can for this section, and I'm looking forward to talking with you all again soon.